So now it's going to be a style compared to the very serious and structured style of lectures you had before. So it's going to be even more confusing. Oh. So is there anything you want to come back to here? Okay, so now this is bonus material. So bonus material is less about numerical methods, or more or less. So bonus material number 1 is convergence of Rayleigh-Schrödinger series. And bonus material number 2 is going to be how to compute gradients. And then if I have time, please ask questions. How to compute gradients. Yeah, interesting things to say about that. Anyway, so, okay, let me just give a brief introduction to resolvent method, green function methods, complex analytic function methods for eigenvalue problems. Okay, so if you are rusty on complex analysis, let me recommend the notes I made 3 years ago for the mini school, 3-4 years ago. I don't know. For the mini school here. I was young at the time and had time to prepare lecture notes. So it's on my webpage. Okay, so the main thing is that this is a nice object to look at. So this is what in math we call the resolvent. And one of the many things that in physics you call green functions. Maybe it's like the easiest type of green function. So I'm not doing any many-body things. This is the green function in the mathematical sense of you solve an equation. So what is this? This I will call RZ. This is the resolvent. Okay, why not? It's the inverse of an operator. Why is this useful? Well, I mean, say you have eigenvalues here. The eigenvalues are the poles of the resolvent. This is rather easy to see because 1 over z minus h is the sum of the I, 1 over z minus lambda I, vi. Okay, so clearly, the eigenvalues are the poles. There's a number of interesting things you can do with this. So when you have a meromorphic function, so this is a meromorphic function, this is all in finite dimension. If you're in infinite dimension, then fun begins, because then you have continuous spectrum, and the resolvent has a very nice structure. Maybe it has a singularity, maybe you can continue against the singularity. You can do fun stuff. So in finite dimension, it's easy, meromorphic, you have poles at the eigenvalue. Oh, yes. So meromorphic is holomorphic except at singularities. So it just has isolated poles. What is meromorphic, you ask? So meromorphic is analytic. Sorry, what is holomorphic? Sorry, holomorphic is analytic. Analytic is complex derivable and differentiable, and it's the same as expandable in Fourier series. There's a very deep theorem that you can find in my lecture notes. Okay, so yes. So now fun stuff you can do, for instance, you can compute this kind of contour integrals. Okay, let me call this C. And if I compute this contour integral, easy. So I remind you, this is a very weird object. This contour integral, it's an integral of complex things. So you integrate this and you multiply by this complex number dz. So you do this in bits. You take a Riemann approximation, for instance, and you at each point you multiply the complex number that you want to integrate with the direction dz. Okay, so it involves complex multiplication, so it's a very weird integral, but nevertheless it's super useful because you've got the Cauchy theorem. The Cauchy theorem tells you, okay, I'm not going to recall this because it will take too much time, but if you hopefully you know this. So the Cauchy theorem says that the integral of a contour of a function f of z is given by 2 pi I, the sum of the residues, say, of the residuals at J. So what is the residue? So this is, if you have a f is meromorphic, if f is meromorphic, so it's an analytic function except at singularities. And so you simply look at how many singularities you enclose, and you sum at each singularity you enclose, you sum what's in this. So basically, I mean, this is just a fancy generalization of this. If you have a function f of z0, dv, this is equal to f of z0. If f analytic. So if f is analytic, then this is a meromorphic function that has a single singularity at z0. And if z0 belongs to the integral of the contour, the interior of the contour. Yes. Yes. Sorry. Thank you. I mean, it's true it's true in either way, but it's more interesting this way. Okay, and this, how do you see? I mean, the fundamental bit is the Cauchy theorem that tells you that if you have an integral and has no singularity, then you can shrink that integral down to nothing and then 0. Okay, this is the important bit. And then if you have an integral like that, you can shrink into the singularities and you can compute explicitly the integral near the singularity, and you find this. Okay, I'm not going to recall this. I'm just going to say that this, if you compute this, what is it? Well, I mean, you look at the singularities of this guy. This has singularities inside, so you just sum all the singularities inside, and what you sum is the residue. The residue is this guy. Okay, residue is what's left after you boil your solution or whatever. So this is 2 pi I, the sum over J such that lambda J is in C. When I say is in C, I mean belongs to the interior of C of Vj. This is a rather nice formula. If I integrate this resolvent, which is just the inverse, yes. No, divided by nothing. Sorry? No. So there's no lambda J because, okay, either you split this sum. Yeah, you split this sum. Yeah, you can see this. You split this sum. Either there's something inside, it's either the eigenvalue is inside, in which case you have an integral with a singularity inside, and therefore you pick up a factor of 2 pi I. Or if there's nothing, times vi. Or if there's nothing, you just pick up a factor of 0. Okay. So that's a rather nice formula. It tells you that you can get the spectral projector, okay, the projector on those two states, by integrating a resolvent. So the first thing is that maybe you can use this for numerical methods. It's one thing you could do, right? So if you want to find these two eigenvectors, you compute this integral, you apply it to a set of random vectors, and then maybe you normalize them or something, or you do a Rayleigh rates inside. And because these two vectors will be, because they will be projected into this eigenspace, and therefore they will span the space. If I have two vectors, two independent vectors that belong to this space, they span the space. So I can do a Rayleigh rates inside, and I can get back the exact eigenvectors. Yes? Sounds reasonable? Sorry? Exactly. So this is, of course, the catch. The catch is that you have to invert this guy. How do you invert this guy? Oh, this is how. So why is it a bad idea? Let's see if you have followed what I've said. Why is this a bad idea to use this formula and to then solve this systems iteratively with like a conjugate gradient or GMRS methods? So let's start again. What is the proposed scheme? The proposed scheme is I take two random eigenvectors, or maybe I just have one. Maybe one eigenvalue. I take a random vector, call it x0. I compute this integral, I discretize this integral. I get a finite sum of resolvents, and therefore I compute the sum of the resolvents times the vector. I orthogonalize, and I get the eigenvectors. I normalize, I get the eigenvector. To do this, I need to solve linear systems. To do the linear systems, I do an iterative method, like a GMS. So let me write this down in more details. I sum over a set of points, z. I sum 1 over z minus h times some vector x0. 1 over nz, the number of points. And this will give me eigenvector. Because it's a projection of x0 onto the eigenvector of interest. And therefore, this is a reasonable numerical method. Yes? Z is complex, sure. I sum over those points. And to do this, to compute this, I do a GMS method. Why is this a bad idea? Remember, Krylov, you can never get out. This stays in the Krylov space. So by trying to be very fancy, I've actually not been that fancy at all, right? Because if I do this with a fancy Krylov methods, this for all z will belong to the Krylov space. And when I sum over this z, it will still belong to the Krylov space. So this is a suboptimal length-short method. Because you stay in the Krylov space, but you are not optimal in the Krylov space the way you would be with a length-short method. The problem is that then you can compare yourself to length-shorts, and length-shorts is better. So for a given number of applications of H, this is probably suboptimal. Okay? So this is a bad idea. The place where this can become a good idea is that maybe you've got a very good preconditioner, and then maybe it's better. Or you've got a sparse matrix and you can use direct solvers, in which case it's better. But if you are simply going to do a simple iterative method, don't do it. You see, it's a good example because this is a very fancy method. You see, it's using complex analysis and so on. But in the end, what you look at when it's actually doing, you see that it just does MATVEX. And if you're doing just MATVEX, you stay in the Krylov space, and therefore you're suboptimal. Yes. Yes, but again, you stay in the subspace. You don't need, but you stay in the subspace. So therefore, you are not much better than length-short method. What is the alpha? Sorry. No, but that doesn't help because if you're in the middle of the spectrum, you cannot pull it out. Yes. No, because it's still the same matrix because the Krylov space of Z minus H is the Krylov space of H. So it's always just applying H. It helps for this thing to have a very cynical view of an algorithm. What is the algorithm actually doing? The algorithm is computing MATVEX. That's it. Yes?
But don't you have a kind of a trade-off between the conditioning number that can hold for, because for solving linear systems, you are sensitive to the conditioning.
Yes.
For the eigenvalue problem, you are sensitive to the gap. So...
Yeah, but this you're also going to be super sensitive to the gap because you're going to invert here, and therefore your contour has to go through the gap. So here it's very badly conditioned. But you see, intrinsically, what you said cannot be true because it's still a suboptimal Langchos method. So Langchos is better than this, always. C'est very argument massue. So this is something that is, this is what I'm insisting on because it looks very simple to say Langchos is optimal. Okay, what does that actually mean, Langchos is optimal? It means that it's really, really optimal. There's not much you can do that it's going to be better. Unless you go to preconditioning. But if you're just going to do MATVEX, okay? Yes. So just because, I mean, this you do for this to compute, you do a GMRS. This is assuming that you do an iterative method for doing this. Yes, to compute this. Because if you do an iterative method, then this guy, the approximation of this guy you will actually compute will be in the kernel. Yes. 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 This was just to illustrate the optimality. Second fun application of this formula, Rayleigh-Ritz perturbation theory converges. Okay, so you all know Rayleigh-Ritz perturbation theory. Okay. I have H0 plus epsilon H1. Maybe you don't call it that, but I'm a mathematician, so I never go without my epsilon. The X. Lambda. So this is a lambda that depends on epsilon. Also, this depends on epsilon. So lambda of epsilon is equal to lambda 0 plus epsilon lambda 1 plus etc. And you know how to compute this, right? You know Hellman-Feynman for this first coefficient. For the second, you get perturbation theory with denominators and so on. I don't need to explain this to you, you know. Does this series converge? Well, if you look at it like this, it's kind of hard to see. You'd have to write down the expansion, and the relational English series get very complicated. There are many, many terms. There's no nice general formula for the nth term. So it's a bit complicated to see. But with this formula, it's much easier. So this guy, I was calling H epsilon, big epsilon. So with this formula, it's much easier. Why? Lambda 1, lambda 2. Yeah, I'm with my indices. This is not. Don't put labels, and therefore it's easier. Why? Because you can get a formula for the lambda and for the eigenvectors by the contour integral. Okay. So lambda epsilon is nothing else but the trace of H epsilon times the integral of 1 minus v minus H epsilon dz. Yes. No, this is just for theory. This is just for theory. It's just to prove you pick any contour that goes through the gap. This is not for numerics. So why does this help me? Because it's easy to see that this is analytic as a function of a z. Okay, remember we said this function was analytic. How do we prove that this is analytic again? Well, z minus h epsilon. This is 1 over z minus h0, epsilon h1. Sorry, it's this plus 1 over z minus h0, epsilon h1, 1 over z minus. Yes. You know this as Dyson series, probably. This is green function, so G is G0 plus G0 V G0 plus so on and so forth. Yes. So therefore, it's analytic. This converges. We've said this, I don't know if it was yesterday or Monday. We saw that this series converged for epsilon small enough. Okay. So this is analytic as a function of z, as a function of epsilon. And therefore, when I integrate a function with respect to another to a parameter, it stays analytic as a function of epsilon. You can see that just by expansion. Yes. This is the next part. Yeah. No, the radius convergence is not zero. This is what I just proved. Yes. So here, what I proved is theorem. If lambda, okay, if there's a gap for H0, converges for epsilon small. So of course, this is finite dimensional. This is for matrices. If you do this for operators, so if you do crazy things like minus Laplacian 1 minus over x, and then you have the good idea to do something like this, maybe. Okay, this is Stark effects. So you put this Stark. Yeah. This hydrogen, you put an electric field, you look at how it moves. This is not covered at all. I mean, this is a very, very bad example. You introduce continuous spectrum, everything breaks down, so this does not work, even if you've got a gap. But I'm not talking about this, I'm talking about matrices. Now, I mean, there are cases where this method of proof, this method of proof was actually introduced by Cato, as far as I know, to prove perturbation theory for operators, so in the infinite dimensional setting. But what you need for this to work is that you need this guy to be bounded. Okay. And if this guy is bounded, then you can do the series. Here it doesn't work because this guy is not bounded. If you've got Cato calls a relative perturbation, or I don't know what they call it. In modern language, it would be a relatively bounded perturbation. Then you're good. Okay. And therefore, relation series. Now to your question, what is the radius of convergence? Well, nice thing about complex stuff is that if the function is analytic, what am I going to draw? I don't know what I'm going to draw. So what is the radius of convergence of this guy? Well, I mean, it is so you know that it converges for epsilon small. So put it like this. So there's some region at which it converges. But now, assuming that this function, assuming that the function is analytic over the whole range, this is a function of epsilon. Assuming that lambda is a function that is analytic up to here, for instance, then if you pick it out here, it also converges. And then you can go on and on until the function is not analytic. But what is the radius of convergence of this guy? In fact, it might not be this, because maybe you've got a singularity here. And if you've got a singularity here, then you converge inside this region, but you do not converge here. Remember, power series, they converge in disks. So theorem, power series converge in disks. So there's a disk inside which it converges, and outside the disk, it doesn't converge. So maybe an example. Epsilon is a very bad name, because I'm going to do the avoided crossing. For the avoided crossing, I need to put a parameter here, so I will call this parameter delta. So probably you've seen this matrix before. H epsilon is equal to this. What are the eigenvalues of this matrix? Do you know the trick for the eigenvalues of matrices like this? Is to write the No, not this trick. The physicist trick. It's to write them as polymatrices. So this is sigma delta sigma. Okay, you've got to help me. What is this one? Sigma y, sigma 2, sigma 1. This one I know it's the 1 and 2. I always get mixed up. Okay. And you know that if you got something like A1 sigma 1, well, some of the I sigma I, the eigenvalues are plus and minus square roots of A1 squared plus A2 squared. This is a very neat trick. So here the eigenvalues are plus and minus square roots of delta squareds plus epsilon squareds. And so this is a very classical example. It's an avoided crossing. I plot things as a function of epsilon is delta. I plot lambda plus and lambda minus as a function of epsilon. I get this avoided crossing with an avoidance of delta. Yes? So what is the radius of convergence of H at 0? So I can expand. I mean, this is an analytic function that I can expand at 0. What is the radius of convergence of this, of the expansion of this at epsilon is equal to 0? Yeah, it's delta. How do you compute this? Because the radius of convergence of a function is the distance to the closest singularity in the complex plane. And this is singular at plus and minus I delta. Okay, and therefore, if you look at it as a function of the complex epsilon, so you see that the complex epsilon appears naturally, even though in the physics of the problem it doesn't. But if you look at it in the complex epsilon plane, there's a singularity at delta, and a singularity at minus delta. And so the radius of convergence is delta. So you see that the radius of convergence is determined essentially by the gap. This delta is the gap here, which is not surprising because with this proof, with the contour also, we had the contour going through the gaps. Yes? So this was a simple linear algebra exercise just to explain a bit how this method can be used. Another fun thing you can do with this is, remember the first day we have this formula? The Gelfand's formula, rho of A being the max of the lambda for lambda in the spectrum of A. Remember this guy? And how do you prove this? Well, if A is diagonalizable, it's very easy. So now A is not symmetric. Usually A is symmetric, but here it's not. So how do you prove this for any A? Well, I mean, if A is diagonalizable, this is very easy to see because you just take the diagonalization and you raise each eigenvalue to the power. And so asymptotically, it should be like this. But if it's not, then a very neat way. So another way is to use the Jordan normal form, but I don't like Jordan normal forms. So what I'm going to do is I'm going to write AN to be the integral of Zn over Z minus A 1 over 2 pi I. I can do this. Why can I do this? I mean, it's a computation. It's the same computation that I did with, I mean, you do the computation with the contour. You find it's this. More generally, any function f of a can be written as 1 over 2 pi integral over the contour. And now this contour is enclose everybody. Maybe the eigenvalues here and here and here. So this is the contour, it encloses everybody. So f of a is f of z over z minus a. Yes. Yes. Organic functions. And therefore, in, you can bound. So now you take for this a circle of radius r, where r is strictly bigger than rho. So if r is strictly bigger than rho, then you've got a to the n is smaller than some constants times rn. And that's the hard bit in proving this formula. Once you know this, everything falls. I mean, because you can do the reverse implication because you can just take an eigenvalue and apply a to the n to the eigenvalue, and you see that you get the reverse inequality. Yes. So this was the MISC chapter, random applications of the analytic methods in linear algebra. Okay, what is this? So this is, I mean, this is mostly useful in quantum chemistry and physics in the context of Green's function, especially when you look at more complicated objects like many-body Green's function, and then you use the analytic properties. But even in very simple linear algebra, you've still got some use of the Green's function and resolvent formalism. Maybe one other thing I write is this nice formula: 1 over z minus a plus b is 1 over z minus a b 1 over z minus, is it this? No, it's not this. Maybe I don't write this, I'm not sure. Because you've got a formula like this, which is the non-perturbative Dyson equation. Should I write it? Ouais, alors c'est 1 sur z moins a plus b, ça vaut 1 sur z moins a fois 1. Ah, okay. Yeah, but... Oui, c'est Dyson, mais du coup, not to try. But anyway, there's a formula like this. Okay, so now I have 30 minutes to kill. So please have questions. So otherwise, I tell you how to compute gradients. Yes? So how to compute gradients? I mean, you probably know some instances of this trick, so I'm just going to tell you the trick that you know in a more general context. Ah, pardon. So this you find in more details, for instance, in my lecture notes from 3 years ago, or in books. Not sure which book. Yeah. I'm sorry?
Where can I see?
On my webpage. Somewhere. Not sure where. Anyway, so how to compute gradients. So I'm going to say something that, okay, how to compute gradients. I have a very complicated function f from Rn to R. And I want to compute gradient f. how do I compute gradient f? So either theoretically or numerically. So in general, I mean, if your function is very, very complicated, so either you do a bunch of work trying to figure out the derivatives, or you do it by finite differences. If you do it by finite differences, what is the cost? So by finite differences, cost is equal to n times cost of f. Yes, you just take it. Sorry. Yeah, okay, so maybe there's a prefactor here, but yeah, simple finite differences. Maybe it's a 2n, I don't know, something like this. Plus 1. Okay? So it would seem like this would be a law of nature, right? If you want to compute a gradient, you have to pay the cost of n times the cost. The very surprising bit, at least to me, maybe not to you, but to me, the very surprising bit is that this is artificial. There exists a method that will compute the gradient of a function, no matter how high the dimension, in asymptotically the cost of one application of f. Do you find this weird or not? Yeah, good. Because me, personally, I find it weird. So I'm going to explain to you the trick. So I'm telling you, there's a trick, a general trick, that can always be used that will reduce the cost of computing the gradient in dimension 10,000 with respect to 10,000 parameters at once for the cost of a single application of f. Yes, magic trick. So which is good because I mean people do this all the time. So for instance, in machine learning, people compute. So machine learning, what is machine learning? Machine learning is that you have data coming in, you have a prediction coming out, and you have parameters in the middle. And inside there's a big machine. Okay. So how do you train this? Meaning, how do you optimize the parameters for your thing to do ChatGPT or whatever it wants to do? Well, you do gradient descent. It's actually that. It's not more than this. So you do gradient descent, meaning you from this you compute something called the loss. And the loss is how far your predictions are from reality. This gives you a single number. And so if you want to do gradient descent on this, you have to compute d loss over d params. This thing is billions. Okay? So if you want, I mean, these models, I mean, the models that people use have billions, literally billions of parameters. So if you want to compute the derivative of the number with respect to this billion of parameters, if you do it like this, you're going to wait a long time. What people do is a trick that allows you to compute the gradient of the loss with respect to all the parameters at once. So in machine learning, they call this backpropagation. In mathematics, they call this adjoint methods. In chemistry, you call it sometimes Lagrangian, and there's tricks with Lagrangians that people use sometimes. And I'm going to try to explain you the trick. Okay? So, what is the trick? So let's take a simple example. So let's say that f of x is equal to c transpose x. No, so f of f of b is equal to c transpose x, where ax is equal to b. Let's do this trick. So what is the gradient of f with respect to b? This you can compute. Not hard to compute. But I want to set this in a more general setting. So you can think this of maybe b is the parameters of your Hamiltonian. C is some observable, like force, property, an energy, something like this. And x is your state of the electrons. Okay, so you have some equation for the state of the electron that depends on the parameters of your Hamiltonian. Here I've taken a linear equation. Again, I really like linear equations because they are so simple, but you can do this with eigenvalues as well. and you take some output quantity. How do you compute the gradient of this? Well, for this one, it's easy. So how do you do this? This is simple. This is explicit. Yeah, so f of v is C transpose X, and X is A minus 1B. So this is also A minus transpose C transpose B. And therefore the gradient is A minus transpose C. Minus transpose means transpose of inverse. Yeah. No? No, because the gradient, by definition, the gradient is the thing such that this is equal to f of b plus scalar product of gradient f of b times delta b. Yes, higher order terms. Right? So that's the gradient. Of course, I mean, this is a very simple example. What happens if instead of having very simple equations like this, you've got, instead of having a simple equation Ax is equal to b, you've got DFT. DFT meaning the mapping that two parameters of the Hamiltonian associate the output density, for instance. Very complicated, very nonlinear problem. Well, it turns out that you can still use the same kind of tricks. So for this, it's useful to do things in boxes. So here, you see the mapping goes like this. From B, X, F. Yeah? So what is the mapping? And here, it's A minus 1. Here, it's C transpose. Meaning, you make the product of X is equal to A minus 1B, and you take the C transpose product. So okay? And so you see a very interesting relationship, which is that in this particular case, the gradient of F was A minus transpose C. So what happens if I see this in a general context? So here I've got that F of B is F1 or F2 of F1 of B. Yes? This is F1, this is F2. So what do you find? You find that the gradient of F is nothing else than F1 prime, F1 transpose, F2 transpose. Yeah, okay, so maybe I write yeah, so here F1 and F2 are functions. I write my big F as a composition of F2 and F2. So F1 of B is equal to A minus 1. The thing, okay, so maybe I don't write it yet. Let's do the trick in the general context and then see what's. So, or actually maybe that's the, so T transpose X. So what is the Jacobian? Oh, okay, so here I'm in dimension n1, here I'm in dimension n2, and here I'm in dimension n3, which turns out to be equal to 1 in this case.
So here that should be F2 of X.
Yes, sorry. Thanks. So n1 is the number of parameters of my Hamiltonian, n2 is the number of degrees of freedom of my electrons, and 1 is the output quantity I'm interested in. Okay. So F1 of B, yeah, okay. So what is the differential df1 of B This is what? This is just a minus 1. So this is from Rn1 to Rn2. What is df2 of B, of X, sorry? It's C transpose. So it goes from Rn2 to R. So I mean, here you see the differential does not depend on the point at which I've taken it. This is just because my equations is linear. If my equations were non-linear, then there would be a dependence. Yes. So now you see here, gradient f is df1 transpose df2 transpose. Okay, and this is in fact a very general thing. So let's go to a more general setting. I still have two boxes. One and two. I have x, I don't know, if x0 coming in, x1, and x2, which is the output. Is this very bad notation? Maybe I be super explicit. I write this with arrows. So f0 to 1 is the transformation that maps x0 to x1. Just so that I don't get confused with indices. Okay, and now I make a perturbation of the input. And I look at the perturbation of the output. This is the thing that I know how to do. This is the thing that you do when you do final differences, for instance. So I make a perturbation delta x0 of the input. I look at what the perturbation x1 is. So delta x1 is what is it? It's f prime 0, 1 of x0 times delta x0. Delta x2 is f prime 1 to 2 of x1 delta x1. And so therefore it's f1 to 2 prime f0 to 1 prime 0. Yes. How do I compute the gradient from this? Here I got the Jacobian of my transformation. So it means that so this is actually good notation. f0 to 2 prime is f1 to 2 prime, f of 0 to 1 prime. And so how do I compute the gradient? This is now, so if there's n0 here, n1 here, and n2 here, this is n0 to n2, which is equal to 1. I want to compute gradient, so my output quantity is a scalar. So how do I compute? So what is this? It's just a row vector. Think in linear algebra terms. Okay, it's a linear map from n0 to 1. So it's a row vector. So how do I compute the gradient? I transpose. Okay. So gradient of f, of the full f, 0 to 2, is nothing else but f prime 0 to 1 transpose f1 to 2 prime transpose. And now you see the trick. So the trick is a very weird one. You start from the end. How do you compute the gradients? to compute the gradient, you start from the end. You see, you have to apply 1 to 2 prime transpose, then 0 to 1 transpose. So you start from the end, you seed it with a perturbation at the end, which is 1. So I'm going to do this very, very nice notation that I like, that nobody likes, but me I like. Is it this? Yes. Yes. So this is delta reversed. It's at lead, okay? It's delta reversed. So what is this delta reverse? It's going to be some perturbation that goes backwards. So you see this perturbation goes forwards. Delta x0 goes forwards. At lead x goes backwards. So in order to compute this gradient in a systematic fashion, without getting lost, of course, this is simple because there are 2 boxes. If you are doing something very, very complicated, there may be 10 boxes, and each box is very complicated. So in order to break down this process into manageable terms, I'm trying to find things that go one way or the other. So at lead x goes backwards. So at lead x1 is f1 to 2 prime transpose at lead x2. And at lead x0 is f0 to 1 prime at lead x1. So in order to compute gradients, you start from the end. You see the perturbation that is at lead x2 is equal to 1, right? Because there's just one thing to perturb, it's the output quantity. You start from the end, no? Transpose things. You start from the end, you propagate it back, you have at lead 1, you propagate it back, you have at lead 0, and at lead 0 is exactly your gradient. This is what people in ML call this back propagation. You have information starting from the end that goes back to the beginning of your code. So this is very weird. These objects are very weird. This transpose is not intuitive at all. I mean, it's not intuitive to take transposes of operations. So what is the interpretation of the Jacobian, of the Jacobian transpose? Well, let's say you have F mapping X to Y. F prime is the map from delta X over delta lambda from some parameter. So I fix a parameter lambda somewhere else to delta Y over delta lambda. Yes, this is what the Jacobian is doing. It's the linearization. So if I have this parameter that actually depends on another parameter, I have some other parameter somewhere else. And if I differentiate with respect to the parameter, so I take a sensitivity, I take a perturbation x dx over d lambda, and I propagate it to y in this fashion. What is F prime transpose? It's very, 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 very tempting to say this as an inverse. It's definitely not an inverse. In order to do F prime transpose, you don't need F prime to be invertible. You don't even need it to be square. Nevertheless, it's very tempting to do it as inverse, but it's not. Yes. I mean, just because chain rule, right? If you have, if you want to compute dy over d lambda, it's df over dx. It's so this is not function space. This is not math notation. It's chemistry notation. It's y is equal to f of x. No, but it's not. Yeah, map. Yeah, mapped. Yes. Yeah, it's good. It's not function space. Otherwise, you put big capitals. Okay, so this is what the chain rule is telling you. So now what is the interpretation of F prime transpose? You see, so F prime, so here you've got delta y is equal to F prime delta x. In the reverse direction, you have atlet x is F prime transpose atlet y. No, sorry. Yes, no, this. So you see, it maps things from y to things from x. So it's very tempting to see it as an inverse, but it's not an inverse. What is it? F prime transpose is the map from delta lambda over dy to delta lambda over dx. So now my lambda is not at the beginning, it's at the end. I have an external parameters, and I want to compute the sensitivity of this parameter lambda with respect to x and y. And assuming I know the perturbation, the sensitivity of lambda with respect to y, I can compute the sensitivity of lambda with respect to x. Yes? Yes. 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 Sort of finite differences, but backwards. Except you cannot do it in a finite difference. You cannot do it in a black box. You have to open your black box.
Okay, but so here, all the, I mean, this is the exact calculation of the derivative.
Yes.
It's no longer finite difference.
No, it's no longer finite difference.
So it is a smart way of doing
Yes.
the analytical calculation.
Yes. 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 So that's a good question. Adjoint people probably it's so in control theory it's been known for ages. So I don't really know who came up. I mean, anytime you see adjoint, it's this trick. It's really this. I would know. So I mean, you know, in control theory you have this adjoint states and so on. So this is exactly the same idea. I wouldn't know who did it first, but it's probably a very, very old idea. Not that old. So, definitely mid-20th century, but maybe not much before.
Are there any assumptions on the complexity of the function?
No, so this is the great way. So this is the great thing. If you have any complicated function, you can always write it as a small function. Something weird like this, maybe with the complicated dependencies and so on, but any complicated function you can always break in smaller boxes. I'm not saying it's easy. In reverse mode, yes. So automatic differentiation comes in two flavors, the easy and the hard. The easy is essentially for finite differences. So this is forward mode autodiff. So you propagate the deltas going forwards. And reverse mode automatic differentiation is you propagate the atlets backwards. This is a lot harder to do because you have to run your code in reverse. Okay, so this is not nice. You see, if your function does, you do something like this, you do something like this. Okay, if you want to do the computation of the gradient, you have to start from here. You have to use the intermediate state. You cannot throw away the results that you had before, for instance. So I'm saying the complexity is the same as the one application of that. The memory cost is much higher because you have to remember any intermediate steps you did. And if you want to do this in an automatic way, you have to register what your code did, keep that in memory, and propagate the applets. Nevertheless, I mean, it's a neat idea. So I think the reason why I'm choosing to speak up to you about this is that I think it's a powerful organizing principle for thinking about how to compute gradients in a general way. So just this basic idea that you have to run your process, not even your code, your process, your equations. You have to run your code in reverse. You have to give names to these intermediate quantities. Okay, I'm using applets. You don't have to use applets. So applets, it works in LaTeX. It doesn't work in Julia. So this is too bad. But it's useful to give them a name and to understand what they mean. And what they mean is the applets, they are sensitivity of the output with respect to the intermediate quantities. And so you define applets of any intermediate quantities and you go back. It gets very, very confusing very, very fast. I mean, here, this is a very simple example, but in practice, it gets very confusing. Okay, so this is a general, no excuse, universal principle. If you are computing your gradients in much more time than it takes for computing your function, you are doing something wrong. Okay, there is a way. I'm not saying it's an easy way, but there is a way. So, roll up your sleeves. So automatic differentiation is very nice because it does everything for you. It's not very nice because it doesn't work. I mean, it's not that it doesn't work. It's not super robust. You have to record everything you do in your code. Language support is patchy. This is hard problem in computer science. Should we do examples of this? You saw the principle. So. Yeah, so one nice relation that helps in order to compute this, because computing this adjoint is not very easy to compute. So in order to do this, one nice principle, so if you have f, again, going from x to y, how do you compute this f prime? It can be tricky for elementary functions. So one nice thing to keep in mind is, so delta y is f prime of delta x. Oh, sorry. F prime of x times delta x. At leds x is f prime of x transpose at led y. What is the relationship between these two quantities? It's this. Maybe I put it on the left. Yeah, that's a neat equation. Sometimes it helps. You see, I mean, this is this. How do you derive this? I mean, you just write it down. Okay. Can we do an example of this? Yeah, for eigenvalue problems. You like eigenvalue problems? So hx is equal to lambda x. Do I call this h or a? I don't remember. Let's do full linear algebra and call it a. I want, so this defines a mapping from a to x, right? I want, so this I call, I don't know, how do I call it, f. And I want to compute f prime of a transpose. So transpose, but see in this very general transpose. The transpose is a transpose in the sense of applications from matrices to vectors. So it's a transpose of tensors, if you want. It's not a transpose of matrices. Understand what I mean? This is a map from R of n times n to Rn. Okay, so it's the transpose as a map from R to Rn, R times n to n. Okay, and I want to compute this transpose. So I have to give it a name to what I'm taking here, and here the natural name is athlete x. There's no standard notation for this. I mean, so people doing AD, they they use something with X bars and X dots, and it gets confusing very, very quickly. The nice thing about the prefix with the athletes and the deltas and so on is that you can do this with names in your code. So you have, I don't know, delta toto est égal à, you can prefix any variable. Of course, if you do Fortrans, you cannot do deltas. Sorry about that. So for Unicode, we use partial. Anyway. So I want to compute this. How do I compute this? Well, I mean, first, instead of computing this, let's compute the easy thing, which is f prime of alpha times delta I. What is this? This you know. This is perturbation theory. What is this? Sorry? X delta X. No, not really, because I mean this is this is the map from A to X. So in order to compute this, you have to solve A plus delta A, X plus delta X, go to lambda plus delta lambda, X plus delta X, first order. Okay. And so what you find is that delta X is minus. Yeah, so I'm assuming that you pick it in the right way. Do you want to do with the eigenvalue instead, or? Yeah, then it gets confusing. Delta X is fine. So delta X is what? Perturbation theory, you know this. This is, you don't write in this way usually, but so I call this a pseudo-inverse of delta AX. What is this weird pseudo-inverse map? The pseudo-inverse is that if you have a matrix like this, so the pseudo-inverse of a symmetric matrix, for instance, is you take the inverse except when you divide by 0, in which case you do 0. Yes? Okay. So it's let's do it explicitly. If A is equal to lambda 1 and so on lambda n, then A minus lambda 1 plus is 0 here, 1 over lambda 2 minus lambda 1, etc. I mean, when you write it, usually you write it in chemistry, you write it in a basis, so you write it in the basis of eigenvectors, but you find the same. Okay? So delta X is, well, written it down here. So you see, it's useful to think of this in the abstract. I don't want to pick a basis for A and to compute the elements of these tensors. I could. Okay. I could pick a basis for this, and I could compute this weird F prime ijk. But it would not be very nice. Instead, I think of it like this, as a linear map. Okay, linear maps, you don't have to express them in the basis. You can just write it as a general linear map. It's often nicer. And so how do I compute the adjoint? Well, I use this. So the adjoint, remember, the adjoint is the map from athlete X to athlete A. Okay. So I can use this relationship to write athletes X delta X is equal to athlete A delta A. So what are these inner products? And this is the inner product for vectors. This is the inner product for matrices. So the trace of A transpose B. Okay. And so now what I'm going to do is I want to do this in reverse. So I want to assume that atlet X is known. And I want to assume atlet X is known. Then atlet A is defined by this relationship for all A, for all delta A. Okay. So atlet A delta A is given by what? Is given by this, but now I know delta X as a function of delta A. So this is given by no, what am I doing? Okay, I'm going to mess up. Let's see. Is this even true? Yes, probably. Je l'ai encadré, donc ça doit dire. Atlet A delta A. This is given by so by this relationship. So this delta atlet X, yes, atlet X A minus lambda plus delta A X. Yes, thank you. What's yes?
This is scalar product.
Yes.
And for A, you have a negative.
Yes.
So how do you define this?
So this is equal to trace of atlet A transpose delta A. It's the sum of the entries. Yes. Okay, so it's 12 o'clock, so saved by the bell. So where do I go from this? So this will define for me atlet A, but what's delta X? This is a scalar. Yeah, I've managed to make myself confused. Yeah, sorry, I should not have improvised this. So you want, yeah, no, delta A is known, sorry. Oh, sorry, delta X is known. I want to compute. Here, delta X is known, but delta, oh, sorry, atlet X is known. What is delta A? Yeah, okay. So this is known, okay? So delta A, I know it in a weak sense. In the sense, I know what is atlet A when I test against all the delta A. So I want to rewrite this as the trace of something against delta A. Okay, and that something will be atlet A. Okay, so now I just have to rewrite this expression as being like this. You see, when I say it's confusing, at least to me. So, okay, maybe I don't do it, but you can rewrite this inner product as the trace. You rewrite as the trace, you make you move the thing where you want them to be, and you take the transpose and you write it like this. Yeah. So what is the, okay, but you have to dictate for me. So yes. So X. Yeah, atlet X transpose. Yeah, sorry. Yes, sorry. The trace of atlet X transpose A minus lambda plus, always with a minus, delta A X, and then you use the cyclicity. So this is equal to minus trace of X delta X transpose A minus lambda plus delta A. So now I just have to take the transpose of this whole thing. So this is equal to minus the trace of big thing transpose delta A, and I have to do This is a plus. So A minus lambda plus transpose, but A minus lambda plus is symmetric, and therefore that works out. And so I've got an X transpose and a delta X. No? What did I do? No, okay. Okay, let me stop here. But okay, you can complete the steps. So you find something, transpose, and that's your applet A. And so that gives you the map from delta X, from applet X to applet A. Okay? And then you can do this as an intermediate step. So if you want to compute the gradient of the eigenvector, so I don't know, maybe you want to compute the polarizability of your molecule. So if you want to compute the polarizability of your molecule, it's the derivative of the polarization with respect to whatever parameter you want, a field or something else. But it's a generalized polarizability. You can compute this in one go for all number of parameters you want. So if you want to compute the derivative of the polarization of your molecule with respect to 10,000 parameters, you can using this method. Yes. Probably. Z-vector method. So Z-vector is probably some fancy way of calling the adjoint or the atlet. Yeah. Yes. Yes, you always have to do this when you want to do perturbation theory anyway. Whether you go forwards or backwards, you have to do. Okay, so I stop here. Sorry, yeah. Yeah. No, but I'm sure it has been done before. So Jacques Houillon didn't invent control. I mean, yeah, he did control, but he didn't invent it, did he? So I'm pretty sure you can trace back to that to like optimization research, linear programming, or this community from before that. I'm pretty sure you can do optimal planning or this kind of thing that is like 50s at the latest. I don't know. I would be surprised if it's not for the simplex, for finance like this. No, but linear programming is Danzig, it's in 40s or 50s. So I would assume it's like the 50s. I can try to find, but probably not the 70s. 70s seems too late, but I don't know. Was your review by a French person or? Okay, so maybe it's correct. Okay, so thank you very much. Sorry for being late. Bien, j'ai pas eu. Ok.